So we're going to wrap up section 4.2. I left you with this exercise to fill out the following table and determine what each number in the top row is congruent to mod 4. So we're talking about in a world where 4 is equivalent to 0. So we filled it out this far. We can keep going here. Remember that we can express 6 as 4 plus 2. 4x is 0, so this is going to be equivalent to 2 mod 4. 7 would be 4 plus 3, so this is equivalent to 3 mod 4. 8 is like 4 plus 4, right? This is a multiple of 4. Since 4x is 0, any multiple of 4 is just going to be a multiple of 0. It's going to be 0 itself. All right, what about 9? Well, 9 can be expressed as that same multiple of 4 plus 1, right? 8 plus 1. So this is equivalent to 1. 10 would be 2 times 4 plus 2, right? This x is 0, so this is 2. This is 2 times 4 plus 3, so this is equivalent to 3. And now we're back to 12, which is another multiple of 4. This is 3 times 4. Any multiple of 4 is going to just be 0. And we see what this table looks like now. It starts at 0, 1, 2, 3, and then it cycles back around again. 0, 1, 2, 3, 0, 1, 2, 3, etc. Keep going like that forever. Now, what happens if we try to go in the negative direction? I can probably take a guess that this will keep going using this same pattern here, right? To the left of 0 is a 3. To the left of 3 is a 2. And maybe it'll keep going in that direction, but does that really make sense? Should it make sense? Well, let's try to think about how that might work. So we want to express -1 as some multiple of 4 plus a remainder. Well, what's the closest multiple of 4 that's smaller than -1? That would have to be -4. Right? -4 is a multiple of 4. It's just 4 times -1. Now what's the remainder? What would we have to add to that to get to -1? 3. It makes sense, right? It's 3 more than a multiple of 4. Okay, so -1 is in fact equivalent, -1 is equivalent to 3 mod 4. And similarly for -2, we can express -2 as -4 plus 2, which means -2 is congruent to 2 mod 4 as well. We can keep going in that direction, right? Okay. All right, so let's look at some more examples here. So how does arithmetic work? I mean, we sort of have a sense of how arithmetic works a little bit, but how can we solve equations in modular arithmetic? We have to be a little bit careful because these aren't really equations, they're congruences. They don't work exactly the same as equations. But luckily they do work sort of similarly with addition and subtraction. So let's say we wanted to solve this congruence for x. Now there's going to be infinitely many x values that will make this congruence correct. So we just want to find the single x value that lies between 0 and this should really be 8. 0 and 8. Because remember, everything is going to be equivalent to either 0, 1, 2, 3, 4, 5, 6, 7, or 8 mod 9. Because once we hit 9, that sort of cycles us back around to 0 again. Right? When we're looking mod 9, a 9 acts like a 0. So we're just going to look for the x value that's between 0 and 8. And that'll give us a sense of what other x values would make this equation true, or this congruence true as well. So with addition and subtraction, it works similar to normal solving an equation, where we can get x by itself, in this case by adding 29 to both sides. That leaves us with x over here. And on the right hand side we get 71 mod 9. Okay, well the problem is we want x to be a number between 0 and 8, and this is too big. But all we have to do is figure out what is 71 congruent to mod 9, and we'll have our answer. In other words, let's try to express 71 as a bunch of copies of 9 plus some remainder. Whatever that remainder is, that's going to be what x is equivalent to mod 9. All right, so what's the closest multiple of 9 to 71? Well, 72 is close, but it's too big. We want the closest multiple of 9 that's smaller than 71. So that would be, let's see, 9 times 8 is too big, so it'd have to be 9 times 7, right? We need 7 copies of 9. Okay, so 71 would be, that's 63 is the closest multiple of 9, plus how many more would get us up to 71? Well, we'd have to add an additional 8. So in other words, 8 is the remainder when we divide 71 by 9. 71 divided by 9 has a remainder of 8. And so our solution is just going to be x is equivalent to 8 mod 9. What this means is that any x value that's equivalent to 8 mod 9 is going to solve this original equation, or this original congruence. Any x that's equivalent to 8 mod 9. So 8 itself, but also 17 or 26, right? There's lots of different numbers that are equivalent to 8 mod 9. Any single one of them is going to be a solution to this equation. All right, but what about if our equations are a little more complicated? What if we allow for other operations, like, in this case, multiplication? We want to find an x value such that 2 times x is equivalent to 4 mod 6. So your first intuition might just be to divide both sides by 2, and that would give you a correct solution here, right? If we divide by 2, we'd get x is congruent to 2 mod 6. But we have to be careful when we're solving congruences like this, because there's other solutions that won't look exactly like, dividing both sides by 2. And so one thing that we can do to solve something like this is we know that we're looking for a solution that's somewhere between, so look for any solution x between 0 and 5. Right, 0 and 1 less than the modulus of congruence, because once we hit 6, we're back to 0 again. So my only potential solutions here are the numbers 0, 1, 2, 3, 4, and 5. I'm going to just manually go through and check every single one and see, is 2x equivalent to 4 mod 6, or is it not? So let's just go through and write down what 2x would be for each of these. So 2 times 0 is 0. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, and 2 times 5 is 10. And now what I'm going to do is I'm going to take this column here, and I'm going to find out what is it equivalent to mod 6. In other words, we sometimes call that reducing it mod 6. Right? What's 0 equivalent to mod 6? 0 is just equivalent to 0. Simple enough. Similarly, 2 is equivalent to 2, and 4 is equivalent to 4, because those numbers are less than 6, so nothing changes here. But 6, mod 6, acts like a 0, right? So 6 is actually equivalent to 0 mod 6. What about 8? Well, we can express 8 as 6 plus 2, so our remainder is 2. So 8 is equivalent to 2 mod 6. And what about 10? Well, 10, we can express it as 6 plus 4. And so we have a remainder of 4. So 10 is equivalent to 4 mod 6. We're trying to find any x values such that 2x is congruent to 4 mod 6. So we're going to look for any 4s in this last column here. We get one here, and we get one here. So in fact, there's 2 solutions here. There's 2 different x values between 0 and 5 that satisfy that 2x is equivalent to 4 mod 6, namely when x is equal to 2 and when x is equal to 5. X equivalent to 2 mod 6, and x is equivalent to 5 mod 6. All right, if this is just a regular equation here, it would only have one solution. But when you're looking at congruences in modular arithmetic, sometimes you'll get multiple solutions. So you have to go through and check every single one. All right, cool. All right, one more example. Let's try to solve for x squared plus 3 is congruent to 4 mod 9. All right, well, let's start by trying to get the x term by itself. I'm going to get rid of this 3 by subtracting 3. Remember, addition and subtraction is okay when you're working with congruences. So what I'm looking for is I'm looking for any x values any solution x between 0 and 1 less than the modulus of congruence, right? 0 and 8, because once we get back to 9, 9 is equivalent to 0, and we've looped back around again. All right, so you might just be tempted to take the square root of both sides, right? But it doesn't actually work that way. And so what we want to do, just like before, is list out all of our possible solutions. Okay, so our possible solutions are the numbers 0, 1, 2, 3, 4, 5, 6, 7, and 8. List out what x squared would be for each one of those. So 0, 1, 4, 9, 16, 25, 36, 49, 64. And then finally, I want to see what is x squared equivalent to. What is it equivalent to? Mod 9. So I'm going to reduce everything in this column, mod 9, and look for any solution that's equivalent to 1, right? That's what we're going to be looking for here. Okay, so mod 9, 0 is just equivalent to 0, 1 is equivalent to 1, 4 to 4. But mod 9, 9 acts like a 0. So we're back to 0 here. All right, now it gets a little bit more complicated. Remember, we're trying to express each one of these numbers as a multiple of 9 plus some remainder. So 16 would be 9 plus 7. Is that right? Yeah, 9 plus 7. And so our remainder here would be 7. 25 is 9 times 2, that gets me up to 18, plus another copy of 7. Again? Okay, 7 again. Our remainder 7, so 25 is equivalent to 7 mod 9. 36, what's the closest multiple of 9 to 36? Well, actually, 9 times 4. It is already a multiple of 9. Remember 9 acts like a 0, so this is going to be equivalent to 0 mod 9. All right, what's the closest multiple of 9 to 49? Let's see, we've got 45 is probably the closest, right? 9 times 5 is 45, that's the closest one. 45 plus 4 gets you to 49, so the remainder is 4. And finally, 64, what's the closest multiple of 9 to 64? That would be 63, right? 9 times 7 is 63. Plus 1 more gets you to 64, so the remainder here would be 1. Now remember, we're looking for any x values such that x squared is equivalent to 1 mod 9. So do we have any 1s in this last mod 9 column? We do. We have 1 here, but we also have 1 down here. And so when x is congruent to 1, we have that x squared is equivalent or congruent to 1 mod 9. And when x is equal to 8, we have 8 squared is also going to be congruent to 1 mod 9. So any x value that's equivalent to either 1 or 8 mod 9 is going to satisfy this original equation up here.